Excellent. Well, good afternoon, everybody. Lovely to see you all here. We'll just give it a minute or so in case anybody else is coming in. So while we're getting going, just have a look at the first screen here. I hope you can see that. And on the right, we've got a rock. It's actually a mineral. Now, some of you may be doing geology already, and you may perhaps even recognize this. If you do, then drop it in the chat so we can see if you're following what's going on. So, what is this mineral that we're looking at on the right? Um, it's a extremely common mineral. It is, in fact, the commonest mineral in the Earth's crust. It's not a beautiful example of it. It's sort of brown, but it is crystalline, so we can see some crystal shapes. Any suggestions out there what this mineral is that we're looking at? And it's okay to be wrong. It's absolutely okay to be wrong because you haven't done a geology degree yet, so that's fine. Any suggestions? Oh, we've got a couple of suggestions coming in there. I like that. Any more? It is quartz. Well done, those people who put that in the chat. So it's an extremely common mineral in the Earth's crust. Nothing exceptional there, nothing very exciting, perhaps. But those of you who are doing geology, and I know it won't be all of you, but if you're already doing geology at A level, perhaps your teacher will often be telling you to put things on your diagrams as well as the what you're drawing. So what is missing from this image on the right here? What are we missing from the image that you would, in your geology notebook, you'd want to add to that image? Something very critical missing on this image at the moment. Okay, got one suggestion from Sam. Anyone else? Well, you're completely right, Sam. We're missing a scale. Okay, it's really important to put scales on your diagrams because otherwise you don't know how big something is. So let's put a scale on that diagram. Okay, there's me for scale. And that is one of the biggest samples of quartz crystals cluster in the world. So it's rather larger than you probably expected, and that's why you put a scale on a diagram. Right, let's get going with the talk. So, uh, first of all, a little bit about me. I'm a professor of applied geology at the University of Leicester, and my teaching revolves around mineral resources. And so, in the second year, I teach a module on critical metals for net zero. And we can see some of the content there on the left. So we need a whole load of metals to build things like wind turbines, solar panels, batteries for electric cars. And we're going to need these metals, some of which we haven't mined before, and all of which we're going to need in much greater quantity than we've previously been mining them. So the question is, how are we going to find them? Okay, and it will come down to some of you perhaps. And how can we get them without making more of a mess of the planet than we already have? It's absolutely critical that we get these metals so we can develop green energy and reduce carbon emissions, but we don't want to make the planet worse by doing that. So this is the real challenge that we face, and this is the sort of thing that we're teaching you about, and this is the second year module when I introduce you to these problems. And then also in the second year, I teach a class on structural geology. So on the right here, looking at how rocks are bended and squished and fractured, and understanding what that tells us about planet Earth. And then in terms of research, again, I work on mineral resources, not just how to find them, but also how to extract the metals more sustainably. I'm a geochemist by background, and I've done work on geochemistry past environments, and that's one of the things I'll talk about in a minute, and also environmental geochemistry and how we affect the environment, the chemistry, and how we may be releasing toxic metals and things into the environment, and again how we can remediate those. Okay, so that's what I do. But more of my background. So I grew up in a small village in Cornwall, and went to a very small school, a small primary school with 6 people in my year group. And I didn't travel very far. Obviously, it was a long time ago. Airplanes had only just been invented. But by the age of 18, I'd only been inside that red circle that you can see on the screen there. So Ireland, a bit of France, and the United Kingdom was my world at the time. And in fact, my first airplane flight was during my degree to go on a field trip to Spain. And what I'm going to enlarge on in this talk really is that geology can be your ticket to the world. And I'll show you some of the places I've been and the things that we do. But I'll also finish off talking about the opportunities for our undergrads actually to go to interesting and exotic places around the world through the links that we have with various organizations and companies around the world. Okay, so this can very much apply to you during your degree and also obviously in a career following on from your degree. Okay, so where have I been now? Geologically, there's a few sort of geolodays in here, but it's mostly research trips that I've been to these places. And when we include places also that I've done research on that I've not necessarily been to, we go even further around the world. So we've got places like Mongolia, Greenland. I've never been to Greenland, but I've done research on rocks from there. Right over in the far right, for example, New Zealand. One of my first research projects was actually doing some geochemistry on rocks from New Zealand and collaborating with a guy who works there, but I've never actually been to New Zealand yet, although I hope to still go there at some point. Okay, but many of these places I have actually been, and for example, on the far right there, I've marked it out especially because it's so small, but the Solomon Islands, right on the Pacific Rim. I did say I was going to talk about those in my talk, but I haven't actually included those. But I've got some other stuff from Peru, Ethiopia, something from Oman, and the Philippines. So I'll be talking about all those places. Okay, and yeah, I even forgot a few places on this plot: Turkey, Costa Rica, Colombia. That would fill it in a bit more. Okay, so let's take you off first of all to Ethiopia, to the north of Ethiopia, a region called Tigray. So this is what it looks like. I don't know if you had any expectations of what Ethiopia is like, or if anybody's even been there, but it is a fantastic, beautiful part of the world. So very dramatic scenery and very wonderful climate. So they advertise it as 13 months of sunshine. Hold on, you say. There's only 12 months in a year. Well, no, there's 13 months in a year if you are Ethiopian. Their calendar has 13 months. And in Ethiopia today, I looked it up and checked it, it is the 1st of the 5th, 2017. They have a different calendar and it is a different year. So they passed through the millennium a few years after us. Okay, so by and large, it's a very nice climate. It does rain as well. We got pretty wet when we were there too, but it's beautiful country, dramatic, very ancient civilization with its own culture and fantastic, very different alphabet with these fantastic squiggly Amharic script. This is in Axum, this obelisk that's very very famous. And it's a country that has never been colonized in Africa, unlike every other country in Africa that has been colonized. Ethiopia is the one country that has not been colonized. It's been occupied by the Italians and the English for a while, but it is has always been its own country. Uh, Interesting place on the boundary between Africa and Arabia, and a really fantastic place to go and visit. Like I said, beautiful. And because of the Italian influence, they do have fantastic coffee, probably the best in the world. And you probably heard about the Japanese tea ceremony. Well, there's actually an Ethiopian coffee ceremony as well. So this is what this young lady's doing here. So they actually brew the coffee up in front of you, and it is probably the best coffee I've ever had. Okay, so it's well worth visiting. The people are lovely. Here they are in their Sunday best, going off to church. Obviously, there's a guy with a gun. You do see a few guns, so it's a little bit exciting, but it's not dangerous at all. Okay, and there's lots of lovely people, lovely kids around when you're doing your field work. So your main danger in the field work is actually being mobbed by kids who are interested in what you're doing, and they still in this part of Ethiopia they will have not have seen many white people, so they're very interested in the Farangi, they call you, and they'll come over and check you out. So these guys on the right actually. When I went back in 2010 after being there in 2006, these guys actually remembered me from the first visit I'd been there and said, "Oh, you were here a few years ago." So it was lovely to be remembered. So why? Why geologically northern Ethiopia? What's interesting about it? Now, what is important is it covers a range of geological time where there are very few outcrops, and it's from the Precambrian. So I've got a little time chart here that goes from 1,000 million years up to 500, and at 500 we're in the Cambrian, so we're in part of the Phanerozoic, where we've got fossils and things in our rocks. But before that, in the Precambrian, there was much less life. But there's a lot going on, and it's a very interesting part of geological time. So back at the beginning of this time chart, we've got a big supercontinent, Rodinia. Okay, and this has been assembled from paleomagnetic evidence. Some of you will know about Pangaea, a more recent supercontinent, but Rodinia is an ancient supercontinent where basically all the landmass was effectively in one massive supercontinent, and that affected things like the climate and ocean circulation, and so it was a very critical part of the planetary evolution. And around 800, Rodinia started to break up. Okay, so we had rifting, fragmentation of this vast supercontinent. So the planet was starting to change. And if you have lots of rifts, you have lots of subduction zones, etc., etc. So the oceans are changing. And interestingly, around that time was the first time we actually developed a land biota, so plants on land. Now, don't get too excited. We're not talking about big plants. Big vascular plants, of course, only developed much later in the Carboniferous, about 300 or so million years ago. But when I say there's a land biota, this is when there were the first mosses and lichens developing on the Earth's surface, and that changed the way erosion happened, for example. And then as we come into around 700 million years ago, we get into this fascinating period of time, the Cryogenian. Okay, so cryogenics, of course, is the science of the very cold, and that's because the Cryogenian is demarked by two major glaciations, the Sturtian and the Maranoan, and they're famous for being hypothesized as being snowball Earth events. So we've got a depiction of it here with the Earth completely frozen from pole to pole. So not just a polar glaciation, but a glaciation that covered the entire Earth. Now, this is a hypothesis. This is not proven, but there is a lot of evidence at the time for glaciation right down to very low latitudes near the equator. So it's quite possible there was a time of complete freezing of the planet. Um, so that clearly will have affected the environment. It will have affected things like the evolution of life. And actually, between those two glaciations is when we potentially have the origin of multicellular animals. Okay, and then we go back to the Maranoan at the top of the Cryogenian, another snowball Earth event, perhaps, and then we're into the Ediacaran period. We have a minor glaciation, a polar glaciation in the gas gears, but at the end of the Ediacaran, we have developed this macroscopic Ediacaran fauna. Um, Typified by this example of Charnia here, which is a soft-bodied organism that is preserved in the late Precambrian. And we can actually see examples of that. It was first discovered actually in Charnwood Forest, just outside Leicester. And you can go up there on a Sunday, and if you know where to look, you can actually go and see a Charnian fossil in the field. So these were all soft-bodied organisms. So there's very little preservation of them. But when we got to the Cambrian, things really took off. We had what is called the Cambrian explosion of life. Okay, and this is where we see a vast increase in the diversity of life. Probably perhaps because that was the time at which shells and carapaces were developed by evolution. So we have much better preservation of life at that point. Okay, so it then became an arms race. If someone's got a shell or a carapace, then someone else who wants to eat them needs to develop teeth, and so on and so on. And then we have that evolution of life that we see in the fossil record right up to the present day. So this period, the Neoproterozoic, the end of the Precambrian, is kind of critical for setting the scene for that development of life and the snowball Earth events. And very fortuitously in Ethiopia, what we've got is a sequence that runs from about 800 to about 700 million years. So it's in that period just before running up to the Sturtian glaciation where we have very little information about what was going on. There are probably only a handful of places around the world that have rocks from this age. If we go back through the rock record, there's less and less evidence. And what we found is that Ethiopia has a really good record. So we were trying to understand what was going on in that time period. Okay, so we've got a little geological map here on the left, so you can see where we are relative to Addis, the capital. So we're right up in the north. We take a flight up to Mekelle, and then we are in this area of Neoproterozoic rocks, and we have this Tambian group here, Neoproterozoic sediments in big syncline structures where they're preserved. And how did we know that we're looking at Neoproterozoic rocks? Well, there are a few dates that were available, but also we work out where we are in the stratigraphy by looking at carbon isotopes in carbonate rocks. And there's lots of carbonate rocks here, fortuitously. So we've got a red box here, northern Ethiopia on this time chart. We're now going time upwards. And we can see that red band, which is the carbon isotope signature of the carbonate rocks. Now, we don't need to worry about exactly what that is. There's a horrible squiggly delta symbol there or whatever. It's just the ratio of carbon 13 to carbon 14, and it tells us something about carbon cycling. And most of the time, the carbon isotope values are high in this period. Um, but as we go into the Sturtian glaciation and the later Maranoan glaciation, the carbon isotope values drop off. And clearly, what it's showing is a change in carbon cycling and a change in the global environment. But what's really interesting, as well as the snowball Earth, is actually this pre-snowball Earth period. There's actually a major carbon isotope anomaly to negative values, as you would get in a global glaciation earlier on, around 800 million years, in what is called the bitter springs stage. But this is a time where there isn't any glaciation. So why did carbon isotopes suddenly flip like that for a period of maybe 30 million years and then flip back again to being positive? And this is the big question. We're missing something about what is going on in planet Earth. So what causes the bitter springs stage? It's named after the bitter springs in Australia, where there's another sequence of the same age, but we think we have this in Ethiopia. Um, Well, one suggestion, and it's certainly not been proved, but it's also not been disproved, is you need some sort of drastic global event. And one suggestion is we've had true polar wonder. So I've tried to, I got a little diagram there on the right to try and explain that. So, and that's with the present Earth. So the present Earth, obviously, it's spinning around the pole, and then we have an internal dynamo that gives us our magnetic field that more or less coincides with the pole. And what it's saying is that in true polar wonder, the actual axis of the rotation moves away from the magnetic pole. Okay, and what that means is the whole of the outer part of the Earth above the liquid outer core has rotated away. So the magnetic core stays in the same position, but the outer shell of the Earth from all of the mantle and all of the crust is rotating around that and moving. Okay, and physicists believe this can happen in the right circumstance. And the suggestion is that we've had true polar wonder and the Earth is tilted on its side. We've had this anomaly and then it's actually tilted back. So it's a pretty crazy idea. And being able to prove this or add evidence to it requires that we can see that event in a number of places around the world. And as I said, there's very few sequences of this age around the world. So we said in this early paper, oh look, we've got a sequence from this age, very exciting. And then a whole load of people got interested, and we went back with some other researchers to do some more work. So I said we've got lots of carbonate rocks, beautiful carbonate rocks, including stromatolites here. So if you look at this picture here, this outcrop, this is all limestone, calcium carbonate. But on the left-hand side, hopefully you can see that the layering is actually here vertical. This rock has been tilted up on end. Okay, so we have bedding running more or less vertically here. And then to the right of that, we have this strange rounded structure, and this is our stromatolite. And that is actually telling us that the rock is getting younger to the right. Okay, so what we can do is we can take that image and we can rotate it back into its original orientation. Don't look at the trees now. So we've got the bedding horizontal, and now we have this stromatolite on top, and it's basically like a rock cabbage. It's a layered structure made of calcium carbonate that is built up layer by layer like a cabbage growing on the underlying seafloor. Okay, so technically it's a laminated microbiolite. So it's basically developed by microbes that are causing the precipitation of the calcium carbonate here and cementing these concentric layers as it grows. So it is developed by living organisms, but those organisms are microbes. Okay, and generally in this time period, they're cyanobacteria. So stromatolites are incredibly important for us and the planet because they were where photosynthesis took place for about 2 billion years. They were the main form of life for 2 billion years in the Precambrian. And we had photosynthesis taking place. And as you do that, you're drawing down carbon out of the atmosphere and you're releasing oxygen. Okay, so these structures and the microbes in them are the main cause of oxygenation of planet Earth in the Precambrian. So we kind of need to be quite grateful to them. But we're extracting them out and looking at their carbon isotopes. And they do still occur today. They're very rare today, stromatolites, because they're very sensitive to macroscopic animals and things. But in some environments, such as Shark Bay here, they actually do still occur. And interestingly, I was able to go to Australia just a few weeks after I'd been in the field in Ethiopia, seeing the same thing. So that was pretty cool. Okay, back to Ethiopia. Along with those carbonate rocks that we can do carbon isotopes on, we have volcanic rocks. So hopefully you can see on the left here, just below my pen, you can see a irregular structure with holes in it. So that is actually pumice. Okay, pumice preserved in an ash band in a volcanic layer. And in those volcanic layers, we have zircons that we can date. So that layer there in the middle where those two guys are sitting, some of our collaborators, I've got a label on there, 816 million years. So we actually dated that precise rock layer, and that's right at the bottom of one of these big synclines that contain these carbonate rocks. So we know the age of them. So we were able to put all that together, and it's a very busy diagram. I'm not going to test you on it later. But what we've done here is we've got stratigraphic logs of each different section of these rocks. We've looked at the rock type and the lithologies, and we've taken carbonate rocks out and done carbon isotope measurements. And we've taken rocks out and dated them. So you can see here, I don't know if hopefully you can see my cursor, 815.29 million years. That's the rock I just showed you. So we dated very precisely the age of these carbonates. Okay, and then we have a carbon isotope sequence. We see it in the middle on B that we've developed, and we've got dates on that, and that ties in with the global signature that we see in panel C here. So the yellow points are from Ethiopia, the rest are from northwest Canada, and you can see that they correlate perfectly and are of the same age. So we've got date points that fit in with the ones from Canada. Okay, so that enabled us to publish this major paper in 2015 that said everything was globally synchronous through this exciting bitter spring stage, and that included people from Berkeley, Princeton, and Harvard in the US. So it's pretty cool working with some very big names there in Ethiopia. Okay, we're going to zip on. I need to watch time a bit. So Oman, just one slide on this. Again, looking at carbonates. So here, what are we looking at? We're looking at a slice of ancient ocean, an ophiolite that has been abducted and pushed up onto land rather than be subducted as it normally would be. So we have oceanic crust and some oceanic mantle. And in those ultra basic rocks, groundwater is actually reacting with them and producing hyperalkaline groundwaters, which come out as springs. So this stream here on the left, we're actually seeing the development of calcium carbonate because the spring is calcium hydroxide, pH of about 11. It's basically lime water. So if you've ever done that experiment at school where you blow into lime water and precipitate calcium carbonate. This is what is actually happening in nature. Okay, and this is great. This is atmospheric CO2 that's being sucked out the atmosphere, so very important. So here we were looking at why that occurs and how actually we might enhance that process to draw down more atmospheric CO2 and actually help fix the environment. Okay, let's go to Peru quickly. 20 kilo bar of gold, and that is my hand. Don't know if you can see that's my ring. I've even got a scar on my thumb there. So yeah, that's a 20 kilo bar of gold. I was out in a gold mine in Peru. So any suggestions how much that is worth? 20 million. 20 million what units? Could be about right. Okay, depends whether you're talking about dollars or pounds. Pounds. Okay, no, it's not quite that much. £10,000 is a bit more than that. So okay, good, good. You're thinking big. The answer, of course, is it's worth an awful lot of money. That's all we need to know. But I did check this morning. So gold is about $85 per gram, or about £69 per gram, and there's 20,000 grams there in 20 kilos. So in pounds, we're about 1.4 million pounds. Okay, so not bad to get your hands on. So why was I there? This is a mine in the Andes in Peru, and I was looking at their processing methods. So on the left, we got the processing plant. On the right, you can look down on that from above. The mine is actually about 3,000 feet above the processing plant. So I was up at looking at the mine, and you can see the processing plant there with the river running by it. That's actually the headwaters of the Amazon that goes all the way across into Brazil and out the other side of North America, South America. So while I was there, I was able to go underground in a gold mine, which, as you can imagine, is quite dark. But we can see on the right fairly typical example of gold ore. So we've got lots of fractured quartz there, and then we've got some shiny yellowish material. That's obviously not gold. That's fool's gold, pyrite that occurs with the gold. That is microscopic specks in there. Okay, so yeah, I was out talking to them about their processing, but to get there, you actually have to fly in a little plane from the coast over the Andean mountains, which is rather exciting, and then back out. I was flying down to Lima to get the plane home, and this is it's not a big airport. When I say it's not a big airport, it has chickens running around it, so. This plane will fly in, turn around, and then fly out again. But interestingly, while I was there waiting for the plane, I knew something was going up on because all these trucks pulled up, and these guys with bulletproof jackets pulled out, and so something's up. And yes, they've definitely got guns. So what are they doing? One of the trucks pulled up and they started putting something in the plane. And then I got on the plane. There's only me and somebody else on the plane flying down to Lima. So what else is on the plane, you think? Well, I've just come from a gold mine, so I'm actually on the bullion run. So these little bags were underneath all the seats, each of which contained a gold bar, and there were 13, I think, gold bars on that plane that were then taken off and loaded into this armored van to take it off to the bank. So 13 gold bars, probably worth about 18 million pounds, and I was flying on that plane, so that's quite cool. And yes, to answer the obvious question, I did think about hijacking the plane and flying to Colombia, but as you can see, I'm still here doing geology. Okay, and just to finish off, tell me if I need to hurry up. Just Philippines, I said I'd talk about that. And sometimes we're not always looking at rocks. Sometimes we're looking at the environmental impacts of mining and crushed rocks. And what we're looking at here is mine tailings, the crushed up material that's left over after we've mined it and extracted out most of the metals that we're interested in. This is a big project that I'm running in the Philippines with Filipino partners and partners in the UK. And the problem with these mine tailings is that they are contaminated with residual metals that are toxic, things like copper in there, and also that they can sometimes collapse and fail and cause big disasters. And so we're looking at ways in which to remediate them, to remove the copper and make them less toxic and stabilize them as well. And remarkably, to remediate them and remove the copper, we're actually looking at using citric acid, which we all drink now and again. Every time you have a soft drink, for example, you're drinking citric acid. It's the acid that makes lemons sour. And we're actually using solutions that are about 2% citric acid, which is actually less strong than lemon juice. We're up here in the north of the Philippines. It's a warm tropical environment, beautiful wooded area. So we've got the mine camp here on the right, and down on the left is the tailings dam that is full of copper that we're trying to remediate. And we're doing experiments in tubs here where we're trying to leach out and extract the copper with instrumentation in the tubs to follow what's going on. So we're running these experiments where we're adding in the citric acid, we're letting it react and then letting it come out the bottom, as you see on the right here. And you end up with this beautiful green solution, which actually has copper in it. And the idea is we can extract that and potentially make some money from it and simultaneously remediate these tailings. Okay, but it's a operation where we need big quantities of citric acid, so we're doing some bucket chemistry here. So Sungano here on the left is actually one of our graduates. So he did a geology degree and now he's out here helping me do this project in the Philippines. And on the right here is Dan, one of our other lecturers. So geology field work, you're all mucking in and getting stuff done. We have a little field laboratory, so this is much more exciting than doing chemistry in a lab. We're actually doing it on a table in the field, and it can be quite exciting sometimes when it starts to rain, as it does in tropical countries. So you have all the challenges of dealing with the weather in these exotic places, and certainly it's raining a lot here. But Sungano's enjoying the trip. And just play the other video on the right here. This is looking actually deep. It gets completely flooded out. But the show must go on. And we have all the thrills and spills of field work. So getting stuck on the road because it's too wet, getting flat tires, and driving around in interesting parts of the world where perhaps different views on safety of transport apply. That's not our bag. Okay, and this is where we stay very often. This is the mine camp in the dark, so nice, warm, tropical. Hopefully you can hear in the background the dogs barking, and wait for it. Some beautiful lightning flashes. And then this is the same place in the morning. Where you can, same place in the morning with all the dogs howling and barking and waking you up. And on the right there, you can see the open pit from the mine that was creating the mine tailings that we're working on. So these are places that you're never going to get to on holiday, but the joy of geology is it really takes you to these amazing places. And as I said at the beginning, it's not just staff who are doing this, it's also undergrads. So these are examples over the years of students who've gone to interesting places on work experience or through their fourth year project. Um, uh, Scotland's first gold mine on the right there, Portugal, that was a gold project. Cam and Rob. And Rob is also featured here on the left in Serbia. So he did his fourth year project in Portugal. He then went to work with a company, and they were working in Serbia. And then he was working with Sam, who was doing his fourth year project that year, and gained that experience. And Sam is now working for the same company. We have Ellen here on the right in Brazil with another member of our staff, Dave Holwell, and Dr. Blanks here, who's actually also one of our graduates who did her PhD after doing her master's degree. And we also take students not only to foreign trips, but also to conferences, for example. So here are three students who did projects in Africa, and then we took them to a geological conference in Cape Town for them to present their results. And then obviously the gap around 2000 because of COVID, but we're now back in the field. So we had two students out in Zimbabwe this summer. There they are with me at the mine where we were working. They were doing exploration with local geologists, working with a company that's doing drilling, looking for gold and tungsten, and looking at the drill core, fantastic drill core that's coming out. Okay, so just to finish off, we have an incredible planet that we live on. So maybe you can see more of it. And really studying and working or researching in geology really gives you the opportunity to go to some of these amazing places across the world. And doing a geology degree, you're going to get taught by people who have experience of going to these places and bring that experience back to you. And if you don't want to travel, there are also lots of jobs and research opportunities in geology in the UK too. So if you're interested, what should you do now? Well, first of all, choose a geology degree. Come and visit us. If you're pre-application at the moment, lower sixth or lower, then come on an open day. They run through the summer. Apply to us, hopefully. If you're already holding an offer, then do come and visit us because you can find out lots more about what we can offer. Okay, so that's it. Geology students, if you're already doing geology, have a look at the photo. You should be able to see a dike. You should be maybe see a fault, or even more than one fault, and an unconformity. But that's the end of me. So any questions? Really love to answer any questions you've got on the talk, on studying geology or anything geological. I can also talk about more generally about the degrees if you're interested in knowing about that. Okay, so Sam's asked a question, what would be the best sectors of geology to work in after university in order to travel like this? Well, I work in mineral resources, and we do have a lot of our students who go off doing mineral exploration in interesting and exotic places around the world. So we would equip you to be able to do that. But that's not the only sort of aspect of geology that allows you to travel. So people can work in things like hydrogeology or geotechnical. And again, geology is completely global. We have graduates all around the world. I know one graduate who works in New Zealand in geotechnical field, for example. So there's lots of things you can do depending on what sort of lifestyle you want in those years after graduation. Obviously, mineral exploration can be in quite far-flung, remote places, and maybe not everybody wants to do that. Or some people might want to do that for a few years and then settle down and do something a bit more in one place after that. So there are lots and lots of opportunities depending on what you want to do. Are there any other questions? Anybody else like to? Is seismology an active sector? Definitely. There's people working both passive and active seismology. So passive is obviously just monitoring through existing earthquakes, etc. And that's usually more on the big scale. Um, Active seismology is when you have a source to actually set off and create seismic waves. But I mean, I'm working with geophysicists on this Philippines project, and they're very interested in um, seismic monitoring of tailings dam facilities, for example, because the key thing is really making sure that they don't fall down and bury people. So there's a lot of research at the moment on that in terms of seismic monitoring of structures and things like that. Lots of things you can do. What are the modules like for the geology course? Okay, I'll just, and what would you recommend a sixth form student to do in order to gain experience ready for university courses in geology and other geoscience? Okay, I'll just answer that second one first, if you don't mind. Um, so for us, it's most important that you are interested in geology, but we recognise that a lot of schools around the country don't offer geology A level. If you're able to do it, that's fantastic. And hopefully you're loving it and you know what you're letting yourself in for. But if you're not able to do geology A level, don't worry. You'll probably be doing geography, I suspect, and you're probably finding that you prefer the physical side of geography, and that's probably an indication that geology is going to be right for you. But don't worry over much about trying to get work experience, especially in geology, because that is quite hard to come by at A level. Anything you can do to enhance your experience is good, even if it's just going on holiday to some geologically interesting area. That would be good experience. We're certainly not demanding that you have work experience in geology, so don't worry too much about that. There are some companies that actually run geology field trips, for example, that you can go onto. They're quite good. Obviously, cost money. So, but have a think about those perhaps. What field trips do you take on a geology degree and what are the modules like? Right, I'm going to switch out of this with general information about our degrees. And within that, we've got answers to some of your questions here. So we're part of geography, geology, and the environment, and that allows us to have a really big community of undergrads and staff that work across this whole area. And there's a lot of interrelationships between those different areas. So we're often doing work with physical geographers. We're doing work even with human geographers because we're working in geology on a planet that is populated by people, and the human aspect is also important. Um, Zip on. Okay, so this is the range of degree courses that we do. So we have human geography, geography, BA, geography, BSc, environmental science, physical geography and geology. So that might be good if you're sort of balancing between the two. Geology, BSc, and MGeol, and geology with paleontology. So those are the possible courses that you can take. That's geography. Move over that. So, for example, physical geography and geology is a mix of the two things. So we've got a list of modules here. at the bottom for that. So let's have a look at geology. So example options, major events in the history of life, environmental geoscience, planetary science, physical volcanology, mineral deposits for net zero. That's a very good module. Crustal dynamics, application in microfossils, things like that. Um, okay, and then or you can focus on paleontology in particular, and you'll have more modules in that respect. All right, I've just lost the chat now. Let me find the chat again. There you go. Field trips, right? I think that's next. Okay, so typical first year for geology. Oh, sorry. Typical first year for geology. This is timetable contact. So you have a tutorial module. You have something like evolution of the Earth system, 2 hours of lectures, 1 hour practical, 2 hour workshops. That's 5 hours a week. Paleobiology, another 3 hours per week from core to crust. Oh, sorry. Another 6 hours a week. So you're very busy actually in the first year. You get a lot of contact time. I've never had an undergraduate who's complained they have too much contact time. So here we are, field courses. So we have core field trips in years 1 and 2. So for geology, we take you to Arran in the first year. If you happen to go to Arran with geology A-level group, don't worry, you won't be bored. There's plenty more to learn on that trip. And then in year 2, you go to Spain for more advanced geology training, and also to Anglesey, where we take you for structural geology training. Obviously, costs you need to think about a little bit, but really don't worry about the costs because they are heavily subsidised by the school. So it's £100 in year 1 and £250 in year 2. Okay, so much less than you've been paying at school for any school trip. Third year, you do have to pay more like the full cost of the trips. So, for example, you could go to Tenerife, and that's about £1,000 all in, but a fantastic trip. And I can say that I've been on that. We also have options in the third year to go to Cornwall or to Wales, that's more paleontology, or Northwest Highlands, which is looking at the structure in that area. Okay, any other questions? Okay, can we do a year away as part of the course? That's probably the next slide. You're anticipating me here. Oh, look at that. Perfect timing. Year abroad. Um, So we have an MGEOL option for a year abroad to do your third year of your geology degree in New Zealand. Um, and there are various other options you can do in the global citizen study abroad. I think in that case, the third year doesn't count, whereas New Zealand, your third year does count. Okay, with very low tuition fees. You can also do a year in industry where you would take a year out in the third year to go and work with a company for a year and then come back and complete your degree. And this can work quite well. So people working, for example, with Atkins in environmental consultancy. Does the course include maths modules? Not specifically. We're not going to torture you with maths, okay? We're geologists and we understand you want to do geology, but you will get taught maths, the relevant maths along the way to enable you to tackle geological problems. So any maths you get taught will be relevant and allow you to do bits of geology that are fun and interesting. Okay, so it will be accessible. It will be taught by geologists, not by mathematicians. Okay, any other questions? Don't know how we're doing for time. I think we're pretty much at the hour.
Think we can probably take that last question that's just come in.
Okay, does geology degree touch on most aspects of the field, and is there any opportunity to specialize in a specific subfield? So yeah, so the geology degree you have core modules in years 1 and 2. Um, in year 2, you will have one option, but otherwise you all do the same module. So everybody in the second year will do structural geology with me, whereas they will have the choice of doing mineral deposits for net zero with me or doing a paleontology module in the second year. So if you're interested in paleontology, you can start focusing on that in the second year. If you're interested in more applied geology, you can focus on that in the second year. And then when you come to the third year, there's a big range of modules that allow you to specialize in things that you're particularly interested in. So, for example, we have our volcanology module there in the third year for people who are interested in that. There's more paleontology, there's environmental geoscience. There's a whole range of modules that you can access, and then there are further ones in the fourth year if you choose to stay on and do the fourth year. Is there someone we've been able to email if we think of any more questions? Yes. So our admissions tutors, I might even have that on the next page.
I think it's
Uh,
the second last slide on this PowerPoint.
there we
Yeah.
go. Okay, so our geology admissions tutor is Dr. Mark Rykow, and he's MKR6 at le.ac.uk. But if you don't get that down, you can email geology at Leicester. It will get through to him. You'll be able to find this on the web pages as well. Okay,
And
but
if
yeah, sure. We know you always have questions just after this finishes, and then you think of that afterwards. So please email us at any time. We're always happy to answer your questions.
if you do forget the emails as well, feel free to send an email to us where we sent you the Zoom link from, and we can pass it on from our team to them as well. So don't worry, we'll get your questions across.
Cool. Okay, well, I hope that was interesting and hopefully inspired you a little bit about what you can do with a geology degree. And hopefully, I'll see some of you on an open day, or maybe even in our first year soon.
That's great. Thank you so much, everyone.